consistent with the planned course and make corrections as necessary. A major consideration for the design of the cutter head and teeth was its effectiveness in tunneling through gravel layer. A diameter of less than 65 centimeters meant that gravel could be directly transferred to the debris hopper, while if it were more than 65 centimeters, then the rock would need to be broken up first. The main considerations were to reduce the need for replacement heads, ease of installing replacements, and ability to manage large blocks of gravel. The design of the cutter head had to consider performance in both gravel layer and sandstone layer. A combination configuration that could handle both soft rock and gravel was therefore chosen. A structure of outward radiating spokes was chosen, using a larger opening ratio, so that gravel could be transferred efficiently to the hopper. Central rings and stop blocks were placed between the spokes to prevent gravel pieces larger than 65 centimeters from passing through the cutting face. In considering the diameter of the shield machine, its stability and digging face and debris removal, a partial use of semi-dome and intermediate support design was adopted for the cutter head. The bit configuration for the cutter head can be described as follows: roller cutter, peripheral face bit, cylinder face bit, scrape teeth, central bit, and copy cutter. In addition, hard plates and bit protectors are installed on the shell to protect the bits. The main consideration for this configuration is to ensure that gravel pieces less than 65 centimeters in size are agitated between the cylinder bit and the drive bit, while gravel pieces larger than 65 centimeters are broken up by the roller cutter and then can be transferred to the hopper by the scraping bit. The vertical shaft is the location at which the shield machine begins to tunnel and is where staff and equipment such as shield segments, rails, rail ties, utility pipes, and cables enter the tunnel. It is necessary to establish a construction base on the surface near the vertical shaft. This houses cranes, muck removal equipment, backfill grouting equipment, an area to stack support segments, a storage area for rail tie and track materials, electricity provisioning equipment, and other related facilities in order to ensure that the tunneling goes smoothly. Before departing procedures, the vertical shaft must be fully supported so as to bear the weight of the shield machine and allow for adjustment of the machine's height and gradient when it commences boring. As the mixture of water for soil extraction in the first stage of breaking the surface can easily lead to subsidence, ground treatments are necessary before work begins. Before boring commences, an outer circle must be cut in the retaining wall of the vertical shaft so that a tunnel ring and shield components can be installed. These are made up of thin steel plates that are fixed onto the tunnel wall. On the interior entrance, packing is used to link with the retaining wall, the shield machine, and to support the shield, creating a waterproof barrier. To prevent earth and water seepage into the tunnel when the shield machine begins to operate, safety at this stage is a foremost consideration. At the initial stage, the friction between the shield segments and the soil is not sufficient to provide traction for the shield machine. It is necessary for a reaction base to be placed behind the tail shield in the vertical shaft to give the jacks a fixed point against which to push forward. During tunneling, the motor drives the cutter head. The debris generated fills in the retaining area against the tunnel face and side walls, increasing outward pressure. When this happens, the shield machine's propulsion stabilizes. The screw conveyor draws out the debris, which is then transported to the base of the vertical shaft. Vertical lifters draw up the debris, which is then transferred to skips, where it is temporarily stored. Muck removal procedures are an important step in shield tunneling. If the flow of the debris becomes too sluggish, the pressure in the retaining area falls. This can lead to a looseness in the tunneling wall. To avoid this, the smooth flow of debris must be ensured through the use of additive material. The muck removal procedures use a valve-controlled, beltless screw conveyor system. Two settings are available, depending on whether drilling is taking place in gravel or sandstone layer, so as to avoid gravel blocking the screw mechanism and to facilitate the evacuation of large-diameter rocks. The conveyor mechanism also has 3 outlets and 5 injection openings that can be used in the event of a blockage. To respond to the different rock layer met with during digging, including gravel and wind-eroded sandstone, the screw conveyor can be set to 2 different speed settings. To stabilize the pressure of the shield machine against the drill face and improve flow of debris, and reduce the risk of debris becoming compacted and affecting muck removal procedures, earth pressure shield tunneling often makes use of earth filling equipment, injecting mud around the cutter head and retaining area. This material is churned into the debris. The churning equipment includes the following: 1. Paddles located behind the rotary head. 2. Spokes used to facilitate muck removal. After completing 1 unit of drilling, shield segments will be installed behind the shield tail. These are usually made up of precast steel reinforced concrete or steel ring sections. After the shield units are installed, it is necessary to check the integrity of the structure, which is upheld through its circular form. To prevent seepage between the joins, the segments dovetail into each other over a waterproof seal. When the support sections are completely installed, the seal material is pressed together to form a waterproof barrier. Jacks are placed behind the shield machine when it is ready to begin boring. The placement of the jacks allows for the adjustment in the forward direction of the shield machine. A number of separate jacks are used to avoid concentration of force in a particular area that might cause damage to the shield. The shield segments are generally made from precast steel reinforced concrete, except in a small number of communication tunnels where steel sections are used. The concrete sections are stored until needed in the factory where they are made. Only then are they transported to the construction site. As the precast steel reinforced concrete segments have to withstand enormous pressure, high standards must be maintained during their production. 1. Manufacturing plant for shield segments. As the sections are heavy and easily damaged, selection of a suitable storage area is of great importance. 2. Management of concrete production. All production materials must undergo inspection to ensure that they meet required standards. 3. Management of concrete pouring. Placement of steel must be inspected before the concrete is poured. 4. Management of concrete treatment. Low-pressure steam curing is used to expedite hardening and facilitate removal from the mold. 5. Management of shield spraying. To prevent corrosion and rusting, the ring sections must be sprayed with bitumen or resin. Spraying should take place in a covered facility inside the precast production plant. 6. Management of shield segment storage. Each storage level of the ring sections should be protected by padding to avoid damage. After the shield segments have been assembled, backfilling grouting will commence. The hoisting eyes are used as injection inlets for the backfilling operation, in which a cementing material is poured under pressure into the injection equipment to fill and consolidate the space outside and at the tail ends of the shield. This prevents loosening of the soil and reduces the risk of subsidence. When the tunneling machine approaches its exit point, it must reduce boring speed and exit point ground treatment, and testing must be carried out. Circumference and elevation must be marked before surface breakthrough can begin. To ensure the integrity of the surface area before the tunneling machine exits, a support barrier must be placed around the exit point. The exit point must also be sprayed with concrete. Chamber separation and counterforce support must all be put in place. The counterforce supports and chamber separation barriers can only be removed after the tunneling machine has exited and the exit point has been tested for water seepage and measured. After that, the waterproof seals and pressure plates are installed. Finally, an arrival platform for the tunneling machine is constructed. The machine is pushed into the vertical shaft and disassembled. After that, the tunnel is checked for connectivity, treated against seepage, and any cracks are filled in. Inverted arch and communication paths are constructed, completing the tunneling process. This auxiliary support structure also includes ventilation, lighting, and drainage facilities. The lighting facilities include safety lighting and ventilation vents that provide all the air needed for the tunnels. These vents also serve to preserve wireless communications, which is important for work safety. Careful geological surveys were conducted as the basis for the design of the cutter head. Despite this, unusual geological factors created blockages in the hopper that prevented further progress. After stopping work, it was concluded that there had been insufficient mixing of material in the hopper and a hardening of material in the hopper due to long periods when the machine had been idle. It was necessary to open up the hopper to clear the debris. Before doing this, vacuum wells had to be sunk in the vicinity of the shield machine and the groundwater level lowered to a point at the base of the machine. It was then necessary to conduct water and toxic gas tests and ventilate any harmful substances before the hopper could be opened. An additional stirring blade was added to the inner face of the cutter head and on the bulkhead wall to prevent material in the hopper solidifying. Once operations recommenced, this situation did not recur. When machines 8 and 9 reached the Section 340 communications passage, where surface treatment had been applied, water levels were reduced in preparation for an inspection of the condition of the bits. After tests for toxic gas, it was found that levels of carbon monoxide and methane were in excess of safety standards. Inspection procedures were halted and ventilation shafts were drilled to release the gases. Sensors to monitor toxic gas were also installed at the screw shaft debris outlet so that this situation could be monitored continuously. Ventilation shafts were also added to the tunnel to reduce permeation of the gases and ensure worker safety. The airport section, built using the shield tunneling method, is a key section of the whole project. In total, it made use of 10 work shafts and 8 shield machines. The section includes 4 underground stations and extends for a distance of 7.2 kilometers. Work on this section of the tunnel commenced on April 19, 2006, using 8 shield machines. As of January 29, 2010, 10 sections of tunnel had been completed, with an average progress of 4 to 4.5 meters per day per machine, drilling through gravel layer based on total construction time. This was in line with pre-construction estimates. Subtracting holidays, maintenance days, and work stoppages due to other types of construction work, the machines progressed at 7 to 8 meters a day under proper management. After inspection and correlation of data, it appeared that the cylinder bit, as the first element to come in contact with the digging face, suffered from wear at 2 to 4 times the rate of other bits, which greatly exceeded permitted levels of wear. The peripheral bit, with the exception of damage caused by impacts, suffered wear of only 20% of original estimates. The drive bits, located on the outer edge, had serious wear issues of 1.5 times estimates, while those on the inside had wear of just 20%. Wear on the roller cutter was as expected. In addition, when passing through sandstone layer, the cylinder drive was unable to effectively cut through the rock face. 5-centimeter concentric circular abrasions were created. This had to be repaired by opening the chamber. During construction, the project was subject to quality control and safety supervision of the very highest level. For example, immediate backfill grouting reduced to a minimum the risk of subsidence in airport structures. In the control tower and taxiway area, micropile cutoff walls, reinforced backfill, and secondary grouting were used for reinforced protection. Ground treatments were made in places where the shield machines operate to prevent subsidence. During construction in the vicinity of the control tower and under the taxiway, various automatic monitoring systems were in place to provide a real-time record of the construction process, revealing immediately any effects on the geological or architectural structure of the ground, ensuring that a high level of safety management is achieved. Construction on this section took place in a complex geological environment in which it was necessary to ensure uninterrupted airport services above ground. Through the course of construction, the neatness of the surface environment was maintained and traffic flow was not disrupted in any way. Total subsidence for the tower and taxiway area remained within 0.4 centimeters. An